All right, so in this video, we're going to look at an example where we verify the divergence theorem. If you recall, the divergence theorem states this. And so for our example, we're going to say that our vector field is given in spherical coordinates, right? We're also going to say that our region has constraints that are also given in spherical coordinates. So this is basically what we have. Now, you could actually draw what this region looks like. If you were to do that, it would look something like this. It's basically the top portion of a hemisphere, which has a radius of A. So now, from this vector field, and from this region, we are going to verify that the divergence theorem holds. In other words, we're going to verify that the left-hand integral is equal to the right-hand integral. Now, before we do that, right, it turns out it's going to be really nice if we convert this vector field into Cartesian coordinates, that is, x, y, z coordinates. So if we do that, let me just rewrite this right here. So, converting this into Cartesian coordinates, right, if you convert rho cubed into Cartesian coordinates, you would get, right, so hopefully we can all agree that this is going to be this to the power of 3/2. But for e rho, right, the vector e rho points in the same direction as this vector. And so all we got to do is take this and divide by its magnitude, you would get e rho. And so this is what we have. Now notice, we can take this thing and divide it by this thing, right? These two things have the same base. So in reality, you're just subtracting the exponents. 3/2 minus 1/2 gives you 2/2. And we know that 2/2 is just 1, so we can just get rid of this thing. This is the vector field in Cartesian coordinates. I'm just going to rewrite this back up here. All right, now we're going to verify that these two integrals are equal. We're going to start by evaluating the left-hand integral. Now, to evaluate the left-hand integral, we need the divergence of our vector field. So we got to take the divergence of this thing. Now, if you recall, the formula for divergence is this. So now you can see why we need Cartesian coordinates, because you have x, y, and z, right? We need to identify vx, vy, and vz, right? We need to identify the x, y, z components of this thing, because it's still not super clear what they are. So now I'm going to rewrite this thing back down here, and we're going to determine what these things are. And so to do this, we're just going to expand it out, right? So notice, right, I'm going to distribute this thing for each component. So basically, it would look something like this. Right. And then now I'm going to distribute the x across this thing, the y across this thing, and the z across this thing. That would tell us, completely expanded out, what each of the individual components are. So now we have completely expanded that out. So now you can see what each of the individual components are for our vector field. So really, we now know what they are, and now we can take these partial derivatives. For the first one, it's basically going to be the derivative of this thing with respect to x. So if you take the derivative of this with respect to x, you get. So this is our first partial derivative. Right now we got to take the derivative of this thing with respect to y. If you take the derivative of this thing with respect to y, you get. Likewise, for this one, if you take the derivative of this thing with respect to z, you get this. So now, if you add all of this together, you're going to get this. And we can then factor out a 5. And then at this point, it's actually going to be nice if we convert this back into spherical coordinates, like that. So that's cool. So now we know what our integrand is going to be. And remember, dv is this. But since our integrand is going to be in spherical coordinates, we're going to want to convert this into spherical coordinates. If you recall, you could use the Jacobian for spherical coordinates, right? You could convert this into spherical, it's this. right? So hopefully we all know this. So really we're going to be using this and this. So now that we have these two things, which is the two things that we need, I'm actually going to write out this integral now. We know that we have 3 parts to integrate, right? This is going to be a triple integral. So the divergence is 5 rho squared, and dv is this thing. So then what are our bounds of integration going to be? Well, it's actually going to be really simple for us. Basically, for rho, since rho is simply less than or equal to a, you can imagine the smallest distance from the origin we could have is 0. And the largest distance is a, right? That's the radius of our hemisphere. For phi, it's pretty easy. We're ranging between 0 and pi over 2, right? 0 and pi over 2. And for theta, well, it's 0 to 2 pi, right? We go all the way around along the base in the xy plane, 0 to 2 pi. So if you really think about it, this integral is actually pretty easy to evaluate. Right, I'm just gonna rewrite this so that this is rho to the power of 4. And so it turns out we could actually break this up into 3 separate integrals. So as you can see, this actually makes it pretty easy. This first integral would just be 2 pi. For this integral, this is all it would be. And for the last integral, this is all it would be. And so if we were to evaluate these two things, pretty easy, right? This is what you would get, and hence the result for the left-hand integral is 2 pi a to the 5th. So now we need to evaluate this surface integral and verify that it is in fact equal to the same thing. So really, for the surface of this region, we can really break it up into 2 surfaces, right? We can call the bottom of the hemisphere, right, the flat part, surface 1, and we can call the spherical part, right, that is the top part, surface 2. Now, if you think about it, for the flat part, right, the bottom, the outward unit normal vector is going to point directly downward in the negative z direction. Hence, our unit normal vector will equal negative k. For surface 2, it's pointing radially outward, right? So you can imagine this unit normal vector will equal e rho. So basically, we're decomposing our entire surface into 2 surfaces, which means we're turning this surface integral into a sum of 2 surface integrals. Now, it's going to be useful if we evaluate these 2 dot products at this point. For v dot n1, we can basically think of it as if we're taking this vector and dotting it with this vector. Now really, it's the same thing as taking the k component of this vector and multiplying it by -1, right? So you can imagine the k component of this vector would be x squared plus y squared plus z squared times z. But really, we're taking that thing and multiplying it by -1. That's what this dot product would be. Right? But here's the thing. For surface 1, right, that is the flat part of this thing, z is equal to 0, right? The z-coordinate of this flat part of the surface is equal to 0. Hence, z equals 0 means that this entire thing is 0, which means that the dot product is entirely 0. And because the dot product is 0, you're really integrating 0, which means that this entire integral completely goes away. And so really, our entire surface integral is going to come from the actual spherical part. So now, let's evaluate what this dot product would be. So, instead of using this one, we're going to use this one. Because really, you can think of it as if we're taking this vector and dotting it with this vector. And you can see it's really nice if we think of it that way because, well, they both contain the same unit vector in them. So really, we're taking this vector, dotting it with this vector. It's pretty easy to see that this results in rho cubed. Now, for this particular case, right, for surface 2, rho is equal to the radius of the hemisphere itself. Because really, on surface 2, we're at the radius of the hemisphere, which is A. So rho is literally equal to A. And so this is what our dot product is. So now if we were to rewrite this thing right here, you would get, now because a cubed is a constant, we can pull that to the outside of the integral. And so this is the integral that we're evaluating now. But what is this integral? It's the integral of all, so basically we're summing up all of the surface elements on the hemisphere. In other words, it's just the surface area of the hemisphere. Well, the surface area of a hemisphere is 1/2 the surface area of a sphere, right? But you can see from this that if you were to simplify this, you would get 2 pi a to the 5th. And so that's really it for this problem. We have verified that these two integrals are equivalent to each other. And so this is pretty cool actually. So yeah, this is basically it for this video.